Okay, so we're going to look at moments, center of gravity. I guess at some point we'll talk about stability. We may get to look at momentum. That's it. I'm hearing somebody's music. I'm hearing and it's very loud. It's not music?
No, it's
the
not.
AC? AC? Music. Alright, so maybe. Alright, so what did we do last week? Just do the homework. Homework is to be done at home, that's why it's homework. Alright, so it says Milton gets into his path and current and accelerates to 20 meters per second in 50 seconds. Oh, new student, are you part of this class? You sure? On the phone, on the lollipop, like totally interested in what's happening. What's the name, new student? Elizabeth? Oh. Do you know what we did last week? Yeah. Second new student, what's your name? Kimberly. Okay. Do you know what we did last week? So I'm only to the new student here, right? You don't say, I'm on last week we did X, Y, and Z. Did you do that?
I just realized.
Okay. Nice. Okay. For the new students, okay, and all students who probably don't remember things, okay, what did we do last week?
Force.
Okay, what is a force? Push, pull, or twist. Okay, and what is the look at? Newton laws of motion. And what are those? First one is the law of inertia. Second one is the law of momentum. Third one is the law of action and reaction. Okay, anybody want to elaborate on any one of those?
Law of inertia means that whenever an object is in a state, it wants to remain there, something like that.
Because inertia is the tendency of the body to keep it stable. Okay. External force. So it means that if the object is already moving, it wants to continue moving, right? But if it is stationary, it wants to remain stationary. Okay, and that will happen unless we have some external forces at play. Okay, what else do we look at? Second law. Anybody want to explain that? So the shortening for it is that F is equal to ma, right? But it's called the law of momentum. So what does momentum do with it?
It says something about momentum being proportionate to mass.
To mass?
Force of
the force. The force applied is proportional to the rate of change of the momentum. Okay. Which means that the harder you push something, the faster the momentum will change. Okay, or the change in a meter rate, after meter rate. Okay. What else? What does the third law say? Everybody remember that one usually. Give an example that wasn't given last week.
If you push hard, it's going to move. But if you're strong enough, the car will move. And you pushing the car, the reaction is the car moving after you apply the force.
Karma.
That's so more like the second law. No, that's not what the reaction means. That's not what the reaction means. Okay? Reaction is just another name for the opposing force. Okay? So if I'm pushing on this door here, right? If I'm pushing on this door here, okay, the door should be moving, shouldn't it? Okay, because if I push on this, if I push on the door, it should be moving, but it's not moving. Why? Because Newton is saying that the door is pushing back on my hand with an equal and opposite force. Okay, that is the reaction we're talking about. So me pushing is the action. Okay, and pushing back is the reaction. Okay? So it doesn't mean that if I punch somebody, they punch me back. That's not the type of reaction, okay? So if I punch you, don't punch me back, right? Right? Okay. That's all we did. So it's a visa class. 2 years, that's all we did.
We did a little type of forces.
Look at some types of forces. Oh, I will look at them. Okay. Resultant force. So what is resultant force again?
The result
being exerted, something like that.
Something like that, yeah.
Hold on.
the direction
The
which
force being exerted and in the direction.
Is the and it's the answer last week, you can answer again. It's the net force, okay? And what you get when you consider all of the forces acting, okay? What you are left with, what is overall force, okay? After you consider all of the forces acting, you make it a face. You don't agree or you don't understand, which is it? Oh, Kimberly didn't tell you about me. Okay, I actually talk to students, okay? And they usually talk back, okay? My question to you is that you don't agree or you don't understand? You don't understand?
I never really tell where resultant force being one. Like, don't you just give the KFC thing. We need to get enough on the fun.
no the F and the
Boy.
Where's the formula? Is it FR equals 30 whatever plus fun?
I don't know all of them. They take
I really wanted to go through this homework.
Yeah, man, I'm gonna go through it.
I have a niece.
But that equal 100.
You want your drawing?
Natural. Okay. What's that, 25?
What's that, sir? 25 or 26?
Alright. So it is not said that in do X, Y, or Z. I have a scenario, right? Elizabeth. So, Elizabeth, I have a condition here. About the phones, okay? Whenever I see a student too close to a phone or touching a phone, my heart will beat fast, so I'm gonna start to shake and I feel faintish and all that, okay? I don't want me to faint, you just like, faint the phone, all right? It's not my fault, I didn't ask for the condition, they just develop over time. Side effect of teaching, I suppose. All right, so Elizabeth, I have that Anyway, I'm gonna pick on you know. So I'm sensing some attitude, okay? Drop it because I'm gonna pick on you everything in the class. And the more attitude I get, is the more I pick on you, okay? So I'm telling you, get used to it. So I have this car here, Elizabeth, and I have all sorts of forces acting on it, okay? What is this force? I'm asking everybody, What is this force? Okay, so it is thrust or the driving force. That's why I put FD there, okay? And of course, it is a force provided by the, define what? But I was about to kind of say it. It's a force provided by the engine to propel the car forward. All right?
Hold on, sir. That is the front of the car?
Sorry,
continue.
What
is that?
the steering wheel.
Oh,
But me? So we can't understand steering wheel. Sure. The point is that the car is going that way. Good. Okay. So of course we know that we're gonna have resistive forces. Okay. And remember, resistive forces, it's in the name. It is resisting the motion. Okay. One such resistive force is friction. Okay. And the friction here I'm gonna say is 20 Newton. Okay. Another resistive force is the drag. Okay. And the drag I gave it to be 50 Newton, and the friction force is 20 Newton. All right. What is W? Somebody was asking what W. What could W possibly mean? It's the weight, okay, which you know is a type of force. Okay, the weight of the car. Okay, and what are these two things here? Natural. It's called normal. Normal, you mean? Okay, so it's called normal or normal reaction or just reaction. Okay, and given that the car is moving up or down, we know that the normal should be equal to the weight, okay? But look, I have 25 and 25 here. That's 50, right? That's not equal to W. Why is that so? Did I make a mistake? Am I on read or something? Or
Is it actually not accounting for the weight inside the vehicle, like person?
uh-uh.
Yeah, because I'm on that jump.
Uh-uh. Pardon? No. I put 25, 25 there, which is 50 to show that that's what these two wheels are offering. But the car don't have two wheels alone. Okay. So the other 50 would be on the other side of the car with the other two wheels. All right. Good. I was making sure you're paying attention. All right. I know. I could have just said the normal is 100, but I want to make sure that you're paying attention. Good. All right. Good. Okay, so now these forces are equal. All right, good. And now I can do this because I don't want to mislead anybody. All right. So this will be provided by the two front wheels, two rear wheels. Okay. All right. So we have a lot of forces acting. How do you know what's happening to the car? How do I know it's not going this way, or whatever it's not going down, or whatever the case is? I have to find the resultant, the net force, the overall force that's acting on the car. Understand what everybody? Oh, I thought that a question. All right. Now we know that vertically, okay, the net force is what? The resultant force is what?
100.
The resultant force is going to be
0.
Going to be 0. Why is it? Because what we're saying is that the resultant force, which you can say is the F up plus F. Worst class ever. So if you add the upward forces, okay, and the downward forces, you get the resultant force. Okay, so Fr is equal to F up, which is let's say up is negative, so F up would be minus 100 plus 100 Newton. This gives us 0. And remember, if the resultant force is 0, it either means that the body is not moving at all or it's not accelerating. Okay, so because remember, Fr is equal to m times a. And if Fr is equal to 0, obviously the mass can't be 0 because it exists. Okay, so it must mean that the acceleration is 0, and that's why the resultant force is 0.
Yeah.
And it's true, the car is not moving upwards or downwards. Okay, so we've just found the resultant force vertically. Okay, what about horizontally? How can I find that resultant force? Same way, I add up all the forces, right? Let's make this direction positive. Okay, so therefore Fr is now equal to, I can say F to the left plus F to the right. Okay, so F to the left, I guess, depending on look at it, since you're looking that way, we're gonna make that be the left, right? So we're gonna say it's equal to 50 plus 20, all right, plus the right is 300 Newton. Did I leave out anything? What did I leave out? So this will be negative 50 plus negative 20, which gives us negative 70 plus 300, which is 230 Newton. So we know that the resultant force is 230 Newtons, so and it's positive, which means that the car ends up moving in that direction. Make sense? All right. Suppose I told you that the mass of the car was 300 kilograms, and I asked you to find the acceleration of the car. How would you do that?
Sarah, that some you need to take into consideration like gravitational force and all those.
No, you're overcomplicated. You're chasing a problem. You're overcomplicating it. No. We just found the resultant force. So overall, the car is moving in that direction. The force of this. We just want to know what is the acceleration. So we know that Fr is equal to mass times acceleration. So therefore, 230 is equal to 300 times A. So therefore, A is equal to 230 divided by 300, which is, we don't work with our calculators. To me, we spoke about this already now. Okay, I want nerdy people who will leave the phone at home and walk with their calculators.
0.7 and those
0.7
and 6.
meters per second squared. You understand? All right. So to the homework is similar. To the homework, okay, what don't you understand? Oh. But were you paying attention? That's the first thing. So where did I lose you? The first step? Oh, okay. I said, let's take the scenario further. Suppose I say that the mass of the car is 300 kilograms, and then I ask for the acceleration. What do we do then? We remind ourselves that, hey, force is equal to mass times acceleration. Okay? So force is equal to mass times acceleration. Hello. If it's really time, I'm going to answer it.
I get it now.
Give me this. Oh, okay. Let's say what I don't believe that boss should just say so. All right, so we got force is equal to mass times acceleration. What is the force? 230.
I get it.
Okay, and your acceleration is what you want to find. So it will be 176.
Because you did multiply before, so now you.
So to the homework now. What does it say? Mary?
No.
Milton gets into his parked car, you say? Hand car, okay, good. And accelerates for?
20 meters per second.
2 meters per second for?
50 seconds.
For 50 seconds, okay. In 50 seconds, okay. Then what?
He maintains this velocity for 1 minute before being pulled over by the police. He applies brakes and comes to a stop in 5 seconds. Right. That's it.
That's it. Right.
What is the acceleration of real car?
What's the acceleration?
Changing velocity over time.
Okay, or we can find the gradient, right?
Sure.
Is equal to? Yeah, right now it is equal to? Yeah, which is equal to?
20 minus 20 meters per second.
It gives us?
So why you have cut out this step?
Because by now it should be, fully aware of the steps.
0.4 meters per second.
Alright, and then next.
What is the total distance traveled?
How do you find the total distance traveled? Okay, so the area of this is? Alright, may I erase now?
No.
Alright, over here. I was trying to not do the long way because we have some things to do today, and I think we've been on this topic,
Okay, all right.
But
Skip to
Ramona,
D.
but Ramona, no, because I already paused what I was doing to do it the long way, so you have to suffer.
So just skip to D.
No, we already changed the plan. Okay.
Somebody make it change by the plan.
So I'm waiting until they write everything so I can go from the long way to wait until we reach D. Elizabeth, you know what to do? Yes. No. There is no. Twice, come here. See? Is this you? Do you want to know your name? What is your name? What about it? Oh, so is a mistake? No, it's not me. It's no. I told you only Benicia once. I've seen everything. That's it. So I should take you off of the here then. So let's see updates. I'm gonna remove this one. So you were the one day this was that. That's what name. That. Okay. There is no.
No. I need extra time.
Take a picture of the board.
I can do this in the meantime. Cindy's here. Audrey, Andrew, not here. Joseph. Joseph is here. Oh. Matthew. Tanya. Odin. Henrik. Jason. And Custody working. Jason here? Present. Okay. David. Alexa. Corey. Absent last week.
I watched online.
Oh.
Yes.
So you said you did the homework?
I did.
Look at you being a good student.
I thought that I left work and I raced home like I was home in 20 minutes. And I was like, there was something I had to do today. And I walked around for that. Oh my God, I have class. And then I started to bawl and I was like,
I love it.
class should be online. So I went online and I was like, okay.
Yeah, I hope also cry when I know the homework too. Cara, I think I saw her. Oh, I missed you at the back. I wish I was where do this person is over here. Christopher, Leonard, Oshika, Kurt.
So when I'm online, you don't mark me present, sir?
Pardon?
You don't mark me present when I'm online?
I don't know if you're.
I commented on the
What happened? I don't know who's commenting on.
I understand. Because I asked a question, I thought my question would have actually been answered.
So we better do we assign somebody to do that? All right. So here's a problem I'm discovering. Okay. So there's a WhatsApp group. All right. Is there a rep in this class that will add people to the WhatsApp group?
No.
Okay, so we need to assign one such person. All right, hold on. Let me go.
I think I'm on a stream.
Let me verify. If WhatsApp will only come on. Okay. So Thursday. Okay, here we go. Admin include Carrie B. 79062. Oh, I don't want to. 790. Who's that? Oh, that's that person's not here. Okay, another admin is 278 47. That's you. Okay, so Ramona is an admin, so if you need to be added to the group, just check Ramona. So we
You're
need to,
also admin, sir.
yeah, but I will not be adding people to my phone to add you to the group.
Wow.
I'm in 7 groups at MU and I teach over 300 students. It's for me to add all the students to my phone to add it to the group. When there's somebody that can do it and add me out here, you're being a little bit egocentric. If you were me, would you do that?
Yes, sir. Everyone.
Honestly, you would add the student to you and then they're gonna just leave in 1 year and you're gonna have to do what? Delete all of that? Or keep it for what? They never ever contact you afterwards anyway. So why would anybody sensibly do that, by the way? Let's go there. Alright, so I won't be adding anybody at all to any WhatsApp group. Alright? What we also need to do is assign somebody who will monitor the WhatsApp group to see if person online have any question. Okay? So is that Ramona as well? Alright, Ramona, I guess it's you as well.
I was the only one who replied to Elaine's message.
What did you do?
Alright. So talk to Ramona to be added to the group. People online, Ramona is the person that will answer your question. So good. No, that is settled. May erase now.
Yes.
Oh, since we're on the topic, do not expect me to readily respond as well in the WhatsApp group. If you have a question, maybe you should save it for class time. But I'm telling you straight up, don't expect me to readily answer. Okay, I'm not even trying to be mean, but without getting too personal, I have 3 jobs and I'm a part-time master student, so I have no time. I teach 7 days a week, so don't expect me to be readily answering your messages. If I come here earlier on WhatsApp, I will probably scroll through, but just don't expect to, Alright. And in the past, students also WhatsApp call me. If I may not answer as well because I'm probably in a meeting or teaching a class. Okay? So
And if we call you when we know you're not teaching a class or in a meeting?
when is that? Like at 10 o'clock at night. Yeah, but I was not answering the end. Alright, but people carry feelings and say, so you never answer me, and I'm like, you understand that our lives are completely different, but in your bed snowing, I'm probably out teaching something. Alright? Like on Fridays, I'm here until 9 o'clock at night. Okay? Most of you probably out partying. Right, Leonard? Or getting ready to go to party. Saturday morning I teach Cape Unit 1. CSEC is in the afternoon, 3 to 6. Right. So, back to the homework. Was that 25? 20. 20. Velocity meters per second and time. Alright, so let's tell what's up. I don't know why anybody would want to do that, but okay. I mean, to each his own still. I think you're safer there though. Alright. Okay, so this is supposed to be straight. Well, it's supposed to be straight. Yeah.
We will deem that is straight.
And do that in straight. Alright, so the first question asks for the acceleration. Kimberly, do you understand this? Huh? Sure. Elizabeth? Elizabeth, you understand what's happening?
Leonard?
Alright, David. What is Ramona doing? How do you say it? Shall I see it for her back? All right. So, and then next one, ask for the total list. Oh, we haven't done it yet. So it's 20 over 50, which was 0.4.
Yeah.
And then next one, ask for the total distance traveled. So we're looking at A, B, and C. So the area of A is equal to half base times height is equal to 50 times 20 times 0.5 is equal to what? 100?
500.
500.
Oh, is that one? 500. Then we have B, which is length times width, which is, oh, the 60 times 20, which is
1200.
So I'm hearing. And then we have C, which is another triangle of a base times height is equal to 5 times 20 times 0.5 is equal to 50. And then the total for that is 1750. Okay, do we all get that? I could my class away. What is that? Something by food. Food important, my girl. Food important more than physics? Who say of course? No. Physics, not physics, just physics. Just put physics in there and you're good to go. Not yet. Alright. Like I was telling my students, I wish I were like, like extremely rich. Because I would like make all my students live with me, and then you know what it feels like, to live a good life, right? So if you want like a glass of water, you have to do 5 physics questions. If you want a bar of soap to bathe, you have to do 20 physics questions. Okay? If you want lunch money, it's a home. It's a home. It's not slavery. Some people in life, man. We're good clothes and eating good food. I'm not doing any physics. Bad man.
One rice green for one.
No, I wouldn't say one rice green, like a couple. You get a couple, man. A couple like 10 questions. If you want meat now, you got 10 questions. I wish I were rich, man. Everybody just come and live with me. Eh? Gravy? You know, gravy expensive. That's 50 for this question. Let's go. Next. What do we know? C?
Yes, C, the total time.
Oh, which is just what? That's right. And then what? Oh,
No, that's wrong.
It's wrong. What does it say?
It's a for his motion.
Yeah, for his motion.
Well, yeah, for his motion.
And the total time.
So I was thinking. So are you individual? Are you individual?
You not started to?
I think I'll do what I started. I'm not that bad.
That's what I was wondering why you asked this question.
Yeah, man, I am no
Because it was
math. Okay, man.
It's physics.
It's the first time?
So you have to turn around the day.
Elizabeth has a nice seat there for you, waiting for you.
So you do need a bit of, well, you will, the class is growing exponentially.
You know what? You know what happened? My Saturday class grew to 68, and then I guess parents complain that I guess students complain, so parents complain that it was too large, so they split it. So no one hall of on Saturday because some of them all left the class and want to come back. But
So where did they go?
they went to a different class, a different teacher. So
Wow.
so there. So do not wish for this class to get too big because I have no more time to allot to you guys. So if they so the different class, I get another teacher. Not my fault. All right. So, but it was okay though, but because I stood in the middle and I walk around and I give my trouble and I talk, but somebody complain and then
I didn't hear my name on the
who are you?
brand
Brian what?
Louis.
Louis? Who's that?
Me.
Yeah man. I see what Kenny, but I marked already. The last name is
Louis.
Louis
L-E-W-I-N.
because I see on the system I have Nicholas, Christopher Nicholas, is that you?
No, Nicholas Louis.
Yeah.
That's my little brother.
Should he be in this class too?
He's going to be, just not today.
Might be in a this.
Alright. So, guess what happened? Guess what happened? I see Nicholas Christopher Louis twice with two different telephone numbers. So nothing more than you are your brother for today.
Okay. So what will
So,
you do next week?
which number is yours? Just tell me the first three digits.
Huh?
Tell me the first three digits of your
I
telephone.
have 509.
509. No.
It's my father's sign up, so I don't know which number.
Okay, I see 990.
990.
And then I see a 817 number.
Oh, that's right.
That's okay. So you are the first one.
That's
So
okay.
I'm gonna edit it. Spell it Brian. Brian. I would ask your middle name. I just put Brian.
I mean, it's exactly the one.
Pardon?
Huh?
What did you say? Okay. So have yours. Were you were here last week, don't it?
Yes, sir.
So I'm gonna put you on. So you were present last week and you're present now. Were you here before that?
No.
Alright. You doing here this week?
Does anybody need this?
For the persons who already are in the group, so.
Yeah, if you're in the I think this is being passed on for persons who are not in the group. So if you are in the group, and remember, we have what is it, 10-digit dialing, so please put the 8 to the 6.
Wow.
So now you're alright. Yeah,
Okay.
as in, first might have numbers that are restricted area code, so it's restricted area code.
I don't think they start to issue them as yet.
In Jamaica, it's not yet out.
Yeah, man.
They haven't started to
Not
issue them
yet
yet.
out.
Yeah, man.
No.
Yeah, man. My number of the new area code.
That's not true.
You know my number?
You're in the group, so yeah.
Put them on one phone.
So that's
I am saying, sir, that you do not have it.
I just in trouble. Next question.
Our next question.
D and D ask for what?
Charlie for
Alright, so we asked for the I didn't see it.
The retarding force is also acceleration, re-acceleration. So we're using the same formula.
Alright, so what does retarding mean?
Slowing down.
It's slowing down. So they ask what is supposed to this? Slow it down. How do we find force? Force?
Of course.
Force. So force is mass times acceleration. Okay? Number one, now, pay attention. Now. You want 5 seconds to deal with the business. Alright? So force is equal to mass times acceleration. If it is retarding, then it is slowing down. Give me another name for slowing down. And it is decelerating. Okay? What do you always say deceleration is? Deceleration is, I'd never say opposite. It is negative acceleration. So pretty much we're gonna find the acceleration, but it should be negative. Okay. Where is it slowing down? Between Yasso and Yasso. So it means therefore that we're gonna find the deceleration. And in finding the deceleration, we would have found the negative acceleration or the acceleration while it is slowing down, because it is the retarding force, like the force on the brakes or whatever, that is causing it to slow down. Okay, so what is the acceleration or deceleration? It's not what you were saying, no, rise over run is equal to the rise is 20, just 20.
Meters per second.
Yeah, but just 20.
Negative, oh.
Because it would be, I would run it just a long way, y2 minus y1. Right? So it would be 0 minus 20 over, what is 0 is that? 115 minus 110 is equal to minus 20 over 5, which gives us.
Sir, so why did we forget the fact that there is a mass?
We've just found the acceleration.
Yeah, but
Force is now equal to mass. Did I give you the mass?
no, you didn't.
I gave you the mass, man. What are the listening
That's
to?
that's the man nobody has done the question
I went online and did it.
without the math.
Yes, without the man.
And you get the same answer?
Yes, minus 4.
So.
Okay, that minus 4 is the acceleration.
And I was
Okay,
like,
we haven't
This
tested
is my
the
lunch
process yet. Okay.
Wait,
The teacher gave the math, it's just that all of you did not hear it, okay?
No,
So the
sir.
math is,
Sir.
so once again, the math is, 150 kilograms. The mass is 150 kilograms.
What's that? What's his hand size?
I want.
Oh, it's a hand card now?
I want.
Oh, no.
Alright, so now we can find the force. 150? Yeah, 150. So the force is equal to 150 kilograms times 4 times negative 4, which is equal to 600. Negative 600 newtons. Is it supposed to be negative?
Yeah.
Yes, because it's the retarding force. It's the force acting in the opposite direction. It's opposing the motion, and that's why the motion ends up slowing down. The force ends up slowing down. Okay? Yes, blame it on me. Most didn't even attempt it.
I attempted it a million
They are
times.
mentally attended.
You made, I mentally believe. Alright. Why what? A G. Where do I have a G?
Yeah, kg, 150 kg.
Oh. Because I'm right stylish. Understand this? Let me know when I can continue because I have some slow people in the class. Ramona, alright?
So question A asks for the acceleration, but you calculate the deceleration. I'm saying question E asks for acceleration.
As in this question?
Oh, sorry.
Ready? What's it? Yeah, you hear music too? No. It was something from that. Oh, you're hearing that too? Okay. That's what it was in my head, the clapping that you're hearing. Sharp.
Please go.
That's no big class. There is now. Right. That's why you're getting a test now. Just wait, I'll give you a mobile test. You can do it on the go. Alright, so just so we're on the same page, we're looking at forces, right? Okay, and the entire topic, the entire section deals with dynamics, and dynamics talk about forces. And we know force cause things to move, right? So forces can cause actually three things. Okay, forces can they can change the motion. Okay, so for example, if something is not moving and I apply a force to it, I can cause it to move. Okay, if something is already moving and I apply a force to it, that force can either cause it to accelerate or decelerate or even stop completely. So it can change the motion. The next thing that the force can do, force can change the direction. Okay, the force can change the direction. Okay, right? If like any student crossing the road, okay, and the physics teacher is driving up to that student, you can just give them a nice little hit with the car, and that changes their direction. You know what I'm saying? It's fluid physics. That's all you do. It's fluid physics. Pardon me? Can't get to it. What that mean? Oh, Johnny! No, but we're just talking about physics. We're talking about physics. Similarly, force can change what? Can change the shape. So again, we have a student crossing the street, and we can use the car to just change the shape, All right. So forces do that, right? So we can change the motion, the direction, or the shape of an object. Okay. In today's class, we'll talk about moments. Okay. Not moments in time. Okay. Like the moment you decided to do physics. Okay, and the moment you decide to regret it, right? Right? Good. But not that type of moments, okay? Moments in physics refers to the turning effect of a force. So moments, and remember, in physics, we are lazy people, so everything has a symbol. Symbol for moment is, and believe it or not, it's also capital T. What is capital T in physics? Time, I leave. Time is common T. What is capital T? Temperature. Took you long enough. Somebody messaging you. I know. You know what? Moments. Okay. So moments are the symbol capital T, and it is defined as the turning effect. Turning effect of a force. Right? Okay. Now, what do I mean by turning effect? Okay. Right? I am not necessarily talking about like when it changes the direction of an object per se. But we're saying that the force is applied, okay, and the object, the system changes or turns, I should say, about a pivot. Okay, it is usually a pivot. Okay, another word for a pivot is a fulcrum. Okay, but we're going to explore all of that now. Okay, now let's say I have this door here, right? Okay, and I see a physics student coming to the door. Okay, what do you think I would do? Yeah, no, so man, I wouldn't do that.
So you did that today.
No, I was just demonstrating physics. Honestly, I was demonstrating physics. So if I wanted to close the door, as you say, I would push it in this direction, right? Towards the hinge, right?
No.
Sure.
No.
I like your brand of craziness. Okay, so I'm asking you, if I wanted to close the door, would I push it towards the hinge like that?
No.
Why not?
Because that's where the pivot is.
Yeah, but practically, why not? Why? Okay, it wouldn't close because there wouldn't be any turning effect. Okay, so this is what we mean by the turning effect of a force. Okay, I apply a force, okay, and the object turns. Okay, turning effect. But this is but this is possible because of the pivot. The pivot wasn't there, okay, and I apply a force. Would it turn? It would move from the fall, or maybe, or if you see when I push it towards the class like that, okay, it would move towards you, okay, but it definitely wouldn't turn. So can we all agree that this turning effect or this turning takes place whenever we have a pivot or hinge or fulcrum? All right, good. So we all agree to this. Get one nice mark and okay, no, it's drawing time. Yo. Shut up.
Trying to draw a table.
That's a door.
Oh,
Okay.
Is that aerial view?
As viewed from above, I'm happy somebody appreciates my joy. So this is the door from above. Okay. So this will be the hinge and this will be the door jamb. All right. Good. So and this is the I see. Good. Now what we all agreed that.
Right,
Like the doorknob right there. Sir, hold on to the doorknob for me. Hold it up. And go like this.
I am viewing the door from above. So this is the door I'm viewing from above. So we're starting off there and we're going along there until we reach the hinge. Okay, and of course this is the knob. As viewed from above, you are above it and looking down. Yeah, Jesus. You get it now?
So I think it's because the hinge is so fat.
Everybody's a critic. Everybody's a critic.
No, make a V for them.
A V?
A V, there are V there.
Because it's a round, and then
So just confirm.
That works.
Just
Just
continue.
So you know what's saying now, we're trying to
Anyways,
So we all agree that applying the force in that direction did not cause a turning effect. Okay. When did we see the turning effect? When the force was applied, like say in that direction, don't it? Okay. Now this is the pivot. Okay. And we applied force in that direction, and that caused it to turn. They're all the same page so far? All right. So Leonard sees me struggling to push the door, okay, and he decides to give me some advice. Okay, so he says, Master sir, that's what you would say, right? You would say, Master sir, push the door close to the hinge. Okay, and right now, believe it or not, I am pushing it close to the hinge. Whereas it's barely moving, if at all. Okay, was that sound advice, by the way?
No.
Okay, why
I know
not?
what you were doing.
Why not?
Sir, the door to the
So I'm very close to it, and there isn't any movement, and I want to close it, so that obviously wasn't good. Now, as I go away from the pivot, what notice happening? Okay, it's easier to move. In fact, when I'm furthest, I can give it a little tap right that it actually turns. But when I was close to the pivot, I was pushing it and it was barely moving, if at all. So, can we all agree that the further we are away from the pivot, the easier it is to turn?
Yes, sir.
Okay, all right. So, we can therefore conclude that oh, by the way, let me make sure we don't take anything for granted. You do agree that the harder my force is, the greater the turn effect, don't it? All right. So we can all agree that the turning effect, the moment, is proportional to the force. Can we all agree on that? Or am I making it up as I go along? All right, good. So can we all also agree that moment is proportional to the distance, as in distance from the pivot or fulcrum. Okay, the greater we are from the further we are from the fulcrum, the greater the turning effect. We agree?
Fulcrum or fulcrum?
Fulcrum. Okay. Okay, my brother. So therefore, we can come up with an equation for moments. And the equation is this. Remember, equations are just the physicist way of saying all of this. Okay? So it is the turn effect of a force. So the moment is equal to the force times the distance. If you increase the force, increase the moment. If you increase distance, you increase moment. We can all agree on that? However, it's not just any force, as you can see. When the force was parallel to the door in this case, okay, right? There was no turn effect. So if look here, this is the fulcrum with a different color. That's the fulcrum. Here. This is the distance from the fulcrum. Do we all agree? Okay. It's very important. Okay. Look at the line of action. Okay. Now, this is where the pivot is. This is where the force is acting. Force is acting along that line
Sir,
there.
use the door, please.
So that is the pivot there. Pivot. Okay. And I am pushing. I am applying force at the edge. Okay. So the door is moving like this essentially. It's swinging like that. Or you seeing that? Good. So what I'm saying is what I say. I'm saying this is where the fulcrum is. That's where the force is being applied. Okay? And it's the distance between the force and the fulcrum. Can we all agree on that? Can we also all agree that it makes a 90-degree angle? Okay? So the force is applied at a 90-degree angle from the pivot. And that's when we achieve maximum turning effect. Can we all agree on that?
Yes, sir.
So therefore, when we are writing down the formula for moment, it's important to remember that it's the force multiplied by the perpendicular distance from the pivot. Is that clear? No one answered me.
So is it always right angle?
So the first thing you do is you identify. I'm going to do questions. Okay, so don't fret about. The first thing you do is you identify where is my pivot. Okay, my pivot is there. Okay, where is the force acting that is perpendicular to the pivot? And get that distance, and you're good to go. We are going to do questions, okay?
Sir, what did
If
you
you don't
say
get it
about
now, that's fine.
the perpendicular thing?
What I said was, this equation is the equation of moment, okay? Where moment is equal to the force multiplied by the perpendicular distance from the pivot. So one is it's always from the pivot. So look where the pivot is, look where the force is, and look for a perpendicular distance between them. And that's what you put in the calculator. Am I making sense?
Yes, sir.
All right, okay. I think 3-person answer to that time. All right. Pardon me? I get it. That's why I keep saying we're going to do questions, so don't worry about it.
Yes, sir.
All right. Yes.
Yes, sir. Yes, sir.
Oh, okay. All right. I'm very limited because of the camera thing, so you have to hold it on the right so I can erase the board so I can write something else. Okay. I can't use anywhere beyond this and beyond like right here. So, and then I don't really write so small as you can see. So, and my diagrams are, they deserve the space that's given to them.
I'm gonna put them in the art gallery.
But
We're gonna put them in the art gallery.
I expect it to, so I can become a millionaire. I don't want to do that because that just seems messy and untidy and yeah. Put me in a box. Don't put me in a box, please. But we must finish by now though. Right? Tell the photographer. When they come in class, you'll be taking photos. Oh, awesome. Oh, nice.
Try not to look like that everywhere. Don't break. I do.
But I should charge you then because you're taking a photo of my drawing, of my
Sir, we
work.
already established at the beginning of the class that everyone in here gets this free. You forgot that conversation?
Yeah.
It's an oral contract.
You guys don't deserve any freebies.
We already made the contract.
You're not doing any physics questions to deserve anything. I teach students with nice clothes and something there, and nice shoes. Like, how is that possible? I'm not doing any physics questions. The spirits are losing it. You leave the house barefooted. You want a pair of shoes to wear? You do 200 physics questions. If you do 100, you get one foot to wear. Okay, and nice phones. S8 and S10 and X11 and all those things. You're mad, man. And lunch money. You're mad. All right, let's go. Now, let's look at that scenario, okay? Remember, please don't take anything that happens in this class personal, okay? Just trying to make you learn something, all right?
Are you sure, sir? And I'm so damn big.
That's good. So,
Around your stand.
That's Miss Campbell.
So, the scam is on the seesaw. All right, sure, no problem. All right, so the scam is on the seesaw. All right, and what's the name you student? Bramwell? Okay. Mr. Bramwell decided to go on this side here. Okay? That's Mr. Bramwell. Good. Well, why? See, that's how it's The point is, okay, Muhammad is over here and this camera is over there. Okay. Now, let's say I want that seesaw to be balanced. Okay, I want it to be level. Okay. What can we do in this scenario? What can we? So, see that she's holding up her hand. Yes, Miss Campbell. Who's the person with the greater master? Just in case we have a little down here. Mr. Muhammad, okay, he'll do what? He would move closer to the fulcrum. That's what Miss Campbell is suggesting. Is that true? Would that help to make it level? I'm hearing yes. I'm hearing no.
If you want to get it level.
Right. So
if you slide forward, it's just going to lean more earth.
no. So wait. Please note that is not passing there. He's on his side. She's on her
She would
side.
have to go.
One of the two will have to go to the end.
Wait, what?
Moment proportional to distance.
Right, moment proportional. So you need her to have more moments, right? So you need her to get more distance.
So you give me a different suggestion.
Sir, both of them put over here.
Hold up. Okay. First of all, we haven't. I see your brother. Okay. Amen, my brother. Put on your hand now. All right. So I have not established if this is incorrect or not as yet. Okay. And that is just one suggestion. There isn't just one thing we can do. Okay. The first suggestion is to move Bramwell closer. Okay. And I wanted to flesh out that first before we say anything else. Okay. So you must be commenting on this now. Okay. So I heard yes, they're okay with that, but I also heard no, that won't help to balance it out. I want to hear from the no person, which was Brian. Yes, Brian. You're saying him moving closer would not help, and I'm asking why. You said that.
Because two of them being the triangle is the fulcrum, right? Right, so two of them being at the fulcrum now.
They're not really at it. Oh, I mean,
no, like
when it's moved, okay.
No, when Brown comes close to the fulcrum, it's just going to tip more to her side. It's not going to.
You think so?
Yeah, I think so. If he
Okay.
was to go to the end now and she comes a bit close to the fulcrum, probably.
Ceremony because they're trying to lean early.
Oh yeah.
Sir, is my lean drawing affecting your your visualization?
Well, forget the leading. Bramwell
So isn't
heavy.
it that
Yes, sir.
But that's
You
what
can't
we do
balance
it.
if we're trying to balance it.
It's still
We
lean.
can't not balance if we're trying to balance.
Joy leaning to
But sir, he's
to her side.
Hold up.
the force on the
I get what everybody's saying, so I'm not
You should join with Miss Campbell up in the air and Bramwell at the bottom.
And the lower top.
sir,
Bramwell should be down and Miss Campbell.
Alright. No. Let's go from top of it. Okay. Let's say Miss Campbell is there, okay?
Yeah.
Alright. And let's say Mr. Bramwell goes and he sits somewhere there. Alright. Okay. What I'm saying is this, alright? Okay. Okay, let him go there. Or do you think it will tip now?
She would be up in the air.
because he's heavy on weight.
So you are saying that it will now go like so?
No.
Like so? Or like so? Alright. 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 Okay. We all agree on that?
Yes, sir.
Okay. I can't. I'm not gonna do 6 different drawings, okay? So that's why I'm using the tool now, alright?
Yeah, well, we probably just try to get.
Oh, okay. So she was on it, okay, and then he came and he sat down, and his mass is greater, okay. And we're saying that it's gonna their things gonna feel like this, right? All together now. My question to the class is, okay, what do you think can happen for it to be level again? Okay, Ms. Campbell suggested that Mr. Bramwell moves closer to the pivot. Okay, and some person are saying yes, but Brian was saying no.
Yes,
And we want to see one person is correct and one person is incorrect. So we can establish who is correct and who is incorrect.
The reason why
You are saying?
the reason why we were saying no is because it was lean. So I thought we
Oh,
yeah.
oh, so you're no longer saying no. Are you still saying no?
No, I'm saying no.
All right, good. So I'm taking it, Elizabeth, you have a question? You sure? Something that we're all saying that to make this balance, Mr. Bami needs to come closer.
Yes.
Okay. What
Or Miss Campbell could
what
go-
else can happen is, I mean, that Miss Campbell can go towards that direction. Why? Why are you saying that? Okay. Whenever you're talking to me, talk to me in physics.
So the
Okay.
distance from
So-
what we established. So they
And therefore,
so the force would be less from there.
well, the force will be the same. The force wouldn't change.
I mean, it wouldn't.
Further
Thank you.
away.
Carl is saying it. You start and Carl finish it, okay? You are saying, because I want us to appreciate that in everyday life you live physics. You just don't use the words that you support, the physics words that you're supposed to use, okay? Because you want normal people to understand you. I don't know why you do that. All right? So I want to appreciate that when you move Miss Campbell out here, you are increasing the distance. Okay? If you increase distance, what happens to moments?
No, but sir.
So right now,
No, so we take it into consideration the mass of that.
We're not getting so complicated.
No,
The ones that we should.
let me just hear what he's saying.
no, sir, but I said we take into consideration the mass. Let's say Miss Campbell have a lighter mass
Significantly lighter mass.
compared to that what I wonder. So I say she wouldn't have that much of an impact on the whole training point of the thing because as I'm saying, thing mass is greater, so it's like it's kind of like
No, we're not even saying whether that would work. We're just saying, what do you think would work? Okay? And they're saying, what do you think would work is to put your, because we don't know how long this is, because that's also a thing too, right? Because suppose it needs to be out here to balance it, but it's just that short. Okay? So I'm not asking if it would work, okay? I'm asking, what do you think we'll have to do to get it to be balanced? Okay? You have a question, Mr. Brammer?
No, I was just saying that moving away from the pivot, I have a greater turning force of lifting the seesaw upwards on this kind side.
Ah, it's, so you are where I'm going, right? Good.
Regardless of the mass, because I'm away from the
Right. So remember, moment is equal to force times perpendicular distance. We can't do anything about the force at the moment. Okay. I can't. I'm just gonna put on 500 pounds. All right. But what I can do is I can increase my my moment, the effect of it, the turn effect by increasing the distance. Okay. To increase her turn effect. Okay. Right now she has a weak turn effect, but so I need to increase it. Or I can put him closer to the pivot. Because remember, D is the distance from the pivot. So I'm not saying I'm moving closer to her per se, but it's just closer to the pivot. And by decreasing his distance, I would have decreased his moment, his turn effect. So that's two things we can do. Okay, we can move Mr. Bramwell towards the pivot, or we can move Ms. Campbell away from the pivot. And I'm happy most of us are able to actually see that. What else can we do now? No, we're not moving the pivot. We're not moving the pivot. What else can we do? I can increase the force by doing what? Maybe I'll ask Melissa to go and sit here. Okay, that could also help, wouldn't it be? Because I will be increasing the force. Okay, so I could ask Melissa now.
So you try to get it right.
I always do, right? There you go. So ask Melissa to sit beside her now, and guess what? That would increase the force, and in increase the force, I would have increased the moment. Are you following? All right. Now, Can I do anything with Mr. Bramble? I could do what? It's probably gruesome, but I can go and chop off a piece of his leg, right? Okay, gruesome. You know that's not my option, right? I can chop off his arm or chop off his leg. But the point is, I can reduce his force, right? And therefore that reduces moment. Okay.
There's no way in terms of moving the fulcrum.
No.
No, we wanna move the fulcrum because I mean
It's like the
that,
door
that's
hinge that
that's more to add
the door hinge
instability
from-
than anything else. Okay.
Yeah.
But just assume that the fulcrum is fixed.
Fixed.
All right. That make your lives easier. You won't start to complicate your lives.
Right, because
Alright.
you won't put the door hinge in the middle of the door.
All right. Good. So we have something now called the. Please understand what you are trying to do. You are either trying to increase Ms. Campbell's moment or you are trying to decrease Mr. Brammer's moment. Okay. Now that leads us to what is called the principle of moment. Okay. And this states that principle of moments, and this states that for a system to be in equilibrium, for a system to be in equilibrium, what a mercy, the kindergarten students, and they sit right beside each other. Is Understand, can you help here? My brother. Yeah, so you can't equilibrium, right?
You know?
Well, system to be in equilibrium, the sum of the anti-clockwise moments must be equal to the sum of the anti-clockwise moments.
Must be equal to.
Yeah.
Almost in the figure eight.
Sir, that's it, it's dry.
Wow, birds!
You know, they're just jealous.
Actually get
They're
the
just jealous, yes.
Where's the next photo? One.
It's a flamingo. Everybody's a critic. All right. So, the sum of the anti-clockwise moments must be equal to the sum of the clockwise moments. The sum of the anti-clockwise moments must be equal to the sum of the clockwise moments. All right. Okay. No, I have a bird on a seesaw type of thing. Okay, and there's a box on the other part, right? Okay. So let me ask you a question: is there moments involved here? Because they both the system has a pivot there, right? And we have those two things there. Now, next question is, what is causing the force? Awesome. Okay, the force is being caused by the weight. Because remember, weight is a type of force. So the bird has a weight that is acting. Vertical don't want like that. We can call his weight W1. But the box also has a mass and therefore has a weight which also acts vertically down. We can call that W2. Are you on the same page so far? Okay, so what we are saying is this. By the way, amnesia. Oh, where am I? Who am I? I don't know. But I need somebody to label the distances given all that we have been saying. Somebody? Anybody? Oops, Elizabeth, the market is falling. Could you label the forces, please? Label the distances, sorry. Based on all that we've been talking about, okay? And you can call them D1 for the bird and D2 for the box. Even our attitude on it. Is this complete? I'm asking the class. Is this complete?
Yes, sir.
This just shows me that something is going in that direction, named D1. Okay. Putting another arrow here and closing this and putting this closer to that. Okay. Now that is complete to the axis. Okay. Remember, it's from where the force is acting to where the pivot is, and it must make a right angle. Are you with me? So this one should be like so, right? 2 there, and of course, to there. We good? That means. From where the force is acting, okay? I will know that we're going to follow in a minute, okay? That is something called center of gravity, and the weight usually acts from the center of a uniform object. All right? So, thank you, Elizabeth. This is D1 and D2. Okay? So, what the principle of moment says is this. Oh, before that, my next question. What do you mean by clockwise and anti-clockwise? I don't know what that means. Oh, so we're saying that this kind of motion is anti-clockwise. Oh, it's clockwise. Okay. So this is anti-clockwise. Oh, so it should be going that way for it to be anti-clockwise. Oh, same thing. Sure.
That's the continuous motion of the clock.
So what is that?
That is
Oh, that is anti-clockwise. Okay, good. So we know what clockwise and ACW, anti-clockwise. Okay. So which one of these providing the anti-clockwise moments? Only 3 persons answering. Why? Let me ask again. By the way, you're banned from talking to the You don't want to know. So, what is causing the anti-clockwise movements is right?
So you can determine by just looking at that?
Yes, that's what I'm going to show you now. Okay, so this is the pivot. Failure. Okay, that's the pivot. Okay, the weight of the bird is acting that way. So let's say the box wasn't there. If the box wasn't there, look what happens. This is the bird. The box wasn't there, and the bird goes and sits on it. It turns.
So, sir,
Okay.
There's a box and a bird already there, sir. The bird was lighter than the box.
You see, you asked a question about A, and then you jump to F. Okay, all right. So, can we all agree that the bird is contributing to the anti-clockwise movement because it causes it to turn like so? We all agree on that. And therefore, the box is contributing to the clockwise movement. Good. So we can say that this would cause the anti-clockwise movement, and this would be the clockwise moment. We all agree so far? Yes, Jason. Ask your F question.
Yes, sir. You can agree, sir. I mean that you're just assuming that's what's happening.
Come here, Jason.
It's always that way.
Come here, man. This camera, you have it in your back camera?
Yeah.
Can we walk over with? Do you walk over with class? All right. Stretch your arms out like that. You come here so much the people on the camera can see you. You might break the camera though, but I mean, you know. So, straight.
bend up like.
Lord have mercy. What's wrong with these people, man? Okay, it should be leveled. All right, good. Now, when I apply this, okay, realize that your arm is moving that way.
Yes, sir.
Okay, is that clockwise or anti-clockwise?
Sir, I understand that. But if I was a pivot and something heavier is at this side, it would have
No,
been-
it doesn't. No. What I'm asking is the bag. Okay, I'm asking what is the bag causing? Clockwise or anti-clockwise movement? That's what I'm asking. What is this bag that's right here causing? Clockwise or anti-clockwise? This bag is causing what?
What kind of movement?
Anti-clockwise.
All right.
Okay, put the
You
bag
have
on
something
the
to
banana.
All right. This bag is causing what?
Clockwise.
And they're both there at the same time. So,
Sir,
so
that is
in
when-
this, huh? Is it that I'm not understanding your question? Is that it?
Sir, in my head, if this one,
Let
if I am a, no, wait, no.
Let me hear his question.
So afterward, we will then discuss which is heavier, because the mass won't be equal all the time.
But what I'm saying is that, oh, you can just assume that when there are two objects there.
Because the thing is, even if one is lighter,
Yeah.
both of them still provide moments about them. So even if one cancels out some of the moments of the other one, both of them still have a turning force. So even if one is lighter than the other one, both of them still have a turning force about them.
Turning
And
effect.
then-
And this one will, okay. Oh,
Assisting officer.
yeah. It's because I'm not jumping them door, just simply him not hearing me. It's all right. It's all right. It's all right. I'll put it on. I should put it on.
No, it can be on the ground, it's fine.
All right. So Jason, we good now. All right. So we can all agree that the bird will cause anti-clockwise movement and the box will cause clockwise movement. Now, what the principal movement is saying is that for this thing to be balanced, okay, the clockwise movement must be equal to the anti-clockwise movement. Does that make sense to you? Especially earlier, what we were trying to do, okay, with Mr. Campbell and Miss Campbell and Mr. Bramwell, is that we're trying to get their movements to be equal. Because if the movements are equal, then guess what happens? End up with a balance system, a system in equilibrium. Can we all agree on that? Okay, so suppose I said to you then that the bird, the box has a mass of 600 grams. The 2 is, I don't know, let's say 0.1 meters. The 1, no, the weight of the bird, the mass of the bird is
150 grams.
150 grams, okay? All right. So my question to you, where should the bird land for the system to be in equilibrium? Okay. How are we going to find that? We are first going to say that for this to be in equilibrium, this should be equal to that, right? So look correctly. What does it mean? Okay, it's sigma and it means sum. Okay, in math and physics it means sum. So the sum of the anti-clockwise moments must be equal to the sum of the clockwise moments. Why do I say sum?
The distance and the weight.
So one is positive and one is negative.
No.
Sum means you're doing what? We're adding. Okay, but the equation so far is about multiplying. I said sum because, as in SUM, because in some scenarios there may be more than one force contributing to the movement. For example, suppose the bird decides to lay an egg. Okay? Yes. So for the system to be in equilibrium, you have to also consider the weight of the egg or the mass of the egg. Are on the same page? But not ready for the egg yet. Not time for omelet, I say. So we'd say some of the HCM is equal to some of the clockwise moments. Now, how do I express the anti-clockwise moments? What do I write next?
Negative.
I don't know what.
No.
Who said that?
No.
So you have to multiply by the new, by the
M1
ten,
times
right?
D1 equals to M2 times
What was that?
D.
Stuart?
M1
M1
times D1
times D1
equal to M2
is equal to M2
times
times
D2.
D2. Okay, suppose I tell that you're half right. Okay, can somebody identify what Stuart is missing? I mean, we don't have D1, but that's what we want to find. So let's put it in the equation. All right. But what is Stuart not seeing? Or should I say, what is everybody else also not seeing? Thank you. Okay. I deliberately gave you the mass, but remember, moment is force times distance. You're given the mass, not the force. How can I find the force? The force is the weight. Okay. How do I find the weight? So the weight would be mass times acceleration due to gravity. Are you with me?
Too fast right now.
All right, I'm moving too fast. Let's go. So here's what I'm saying, okay? I am saying that I deliberately give the masses, okay? Because I want you to recognize that moment is equal to what, Ramona?
The force times
Yes.
the distance of perpendicular.
Thank you for answering me. Good. But so we are finding the moments, but moments is not mass times distance, it's force. What is causing the force in this scenario? The weight of the object. So we can say force, which is caused by the weight, is equal to what? Mass times acceleration due to gravity. That's why I find the weight of something. We did this already, right?
No. Ish. Sir, we kind of when we're
Yeah,
wondering.
we don't do it. We don't want to ish me. Okay? What? Will it stop here, sir? Oh, yeah.
So we're asking about when you were saying, like when we say gravity is a force or what.
So wait, so I didn't give this equation?
No, you just gravity not being a force.
I did not?
No.
Yes. But if that you weren't get first class, how can we say no? I'm just showing you. So if I did not, then my bad. We need to explore that some more then. Okay. So let's pause then. Sure I didn't. All right. So let's talk about it for 1 minute. All right. So I believe I said that everything that has mass, okay, and you're exposed to a gravitational field, okay, that gravitational field will pull you toward the center of that larger mass, like a planet. All right. So it means that things that are exposed to a gravitational field have weight. Okay. Weight is a pull of gravity on that mass. So if we can say weight is equal to mass times acceleration due to gravity, which is G, we just call it G. Okay. In every language, some person just call this gravity. Okay, but it's actually acceleration due to gravity. Looky here, people. Force is equal to what? Mass times acceleration. Are we following? Yes. Okay. If we have a mass, if we have a mass and it's within a gravitational field, okay, it is within the gravity of, let's say, Earth, okay, it will accelerate at a particular value. It will accelerate at 10 meters per second squared. We call that G. So the acceleration is G. When the gravitational field acts on a mass, or gravity acts on a mass, we call that weight. Can you appreciate why weight is a type of force? They're the same, but it's being a little bit more specific. Are you with me? All right. So, weight is equal to m times g, and on Earth, g has a specific value of. It's actually 9.81, close to the equator. Okay. However, at this level, at CSEC level, we just usually say 10. We want it up to 10 meters per second squared. It means that everything that falls, okay, will accelerate at 10 meters per second squared. I was talking about the elephant and the mouse. We did that already, right? It's because of the this here. Okay, everything that falls will fall at that acceleration, and also because the mass is exposed to the gravitational field or gravitational force. Okay, m is equal to W is equal to m times g. So whenever you want to find the weight of something, just multiply the mass by 10. And what will our unit be? The unit will obviously be Newton because it's a type of force. Good to go? All right. So in this scenario, we are given the mass and we want the force which is provided by the weight. So therefore we say that we say W is equal to m times g, which is equal to 600 grams times 10 meters per second squared. And we get what? 6,000. Are we go? Oh, that's 6,000 newtons. Okay, are we gone, right? You're on the ball today, man. You're on the ball today. Okay, so this is how we're gone. We're gone clear. Okay.
Which one is that was 600?
The M1, which is the box. Okay, but you are missing something, Leonard. Okay, only one person recognized that. Guess what happened? This is in grams. What's the SI unit for mass? Okay, so we are not paying attention. Again, I deliberately expressed it in grams. Pardon? You all the time. I mean, one time this was talking about Jesus mercy. All right. So we have to change this to kilograms. How do we do that again?
Divide by 1,000.
Okay. So we divide this by 1,000 and I end up with 0.123. So end up with 0.6 kilograms. So it will be 0.6 times the 10, which gives us 6 newtons. Everybody with me so far? Ramona? So therefore, this would be 0.15 kilograms, which is equal to the weight to be what? 0.15 times 10, which is 1.5 newtons. What are you following so far? Kimberly? All right. Elizabeth, you understanding so far? All right. Hello. Write off the note to make the photo. You can what? You can draw the bird. Then you ask an expert to do it for you.
Just draw cats.
All right, so let's go. And I need some space. Do I need space? So, Stuart, what do I need to put here now then? What do I need to put here now then? Symbols. I would say W1 times the right, and I would say W2. Okay, so W1 was what? We got that to be what? So it's 6 Newton times what's the distance? Oh, so we don't know this. D1, okay. And W2 is 1.5 Newton times D2, and D2 is 0.1. On the same page so far? May I erase here so I can continue?
No.
Tell the board I'm not going to work out there, man.
Just put the 6 M down there.
But the people on the camera can't see that.
What about?
Stressing me out.
Sir, you right? So spread out.
Yeah. Yeah.
Continue.
Oh, I can get rid of Miss Campbell. Miss Campbell will get rid of you. So continue up top.
6N.
So 6n times d1 is equal to, what is 1.5 times 0.1? 0.15. Yeah. Newton meters, right? What is Newton? Oh, Newton times meter. Alright. So therefore, d1 is equal to what? 0.15 Newton meters over 6 Newton, which gives me 0.025 meters. So the bird needs to be 0.025 meters.
D1.
Is that? Why does that seem like
The bird will left on the box.
be so?
The other closer than the box.
Okay. No, is that logical? D1 is supposed to be D. Oh, you know, somebody had gone come on. Thank you, Mr. Gabriel. Maybe they say with such attitude. Maybe that's what you said that attitude, bro. Okay. So, my question right now is that logical? Is that expected? Does that make sense? Are we defying the laws of physics and the laws of nature and the laws of the universe? It means that the bird has to be very, 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 very close to the pivot. Is that what you expect?
No.
Okay. Which one have a greater weight? The bird. So do you expect the bird to be? What's in the box? The weight of the box is 1.5. So
that means the bird should have been nearer to the pivot.
So I'm asking, does our answer make sense?
Sir, you see? Hold on. Hold on, sir, wait, hold on. You told us that the box is 600 grams, which is M1. That's what you told us.
Yeah, but it's converted to kilograms.
M1. No, that is the bird.
No, you told us that it is the box.
You said it was
All this W1 and W2.
That's what I was wondering, and I wrote it down.
But you did say it was the box, though. You did say that big number is the box.
That's how I was.
Because that would have made sense then, sir. All you have to do is switch around the W2 over there and put it over there. Just switch them.
Okay, alright, okay. Alright.
Sir, just rub them and start over.
So just rub out the W2.
Yeah, and we get lost when you're on 60 take the zone. So.
Do what?
You can just rub all of them.
Okay, okay. Persons are saying that I thought M1 was the box.
Yeah, you did.
If I did, that was a mistake because I mean I have W1 there, so W1 have to match with M1 and W2 have to match with
You put in those
M2.
last, the M1 thing. Over there, sir, but you did say it was the box, though. Anyway.
Yeah, and what I'm trying to establish is if I do, which I will in the future make several mistakes, okay? If I do, then it was a mistake, but I want you to know that the same page. Oh, yeah, it is, the box is W2. Okay, I'm gonna have an issue going.
And remember, see, the D2 there, that should be changed now to D1. That's why you said it was the box.
D2.
After 600 grams, then you have D2 equals 0.1 meter.
Which is this.
Yes.
Which is for the box.
Okay, look up there.
Look up where? Up where? Up here?
No, yeah, right there, right there.
D2. D2 is, so D2, which one is that? D2 is for this. D2, D2. Okay. And into I am confused as to the next mistake that you're seeing on the board.
So if the box is supposed to be 600, then
okay, we see we're back there. The box is not supposed to be 600.
Then that means that the bird wouldn't be closer.
Yeah, that makes sense.
The distance that the bird is that would be wrangling.
That bird is further
Are
away.
they trying? The bird is further away from the pivot.
The bird, if
The bird is heavier, it would be further away from the pivot.
Okay. I need you to talk to me now, okay? Here's a scenario, Ms. Campbell. Here's a scenario at hand, okay? In the current scenario, what is 6 Newton? What is 1.5 Newton? Okay. Which of those is heavier, way more? All right. So if I have a ledge, a light box, and a heavy bird, what do you think should be very close to the pivot? The box or the bird? The bird. All right. So the box is 0.1 meters away, and the bird we just discovered was 0.02. Is that closer to the pivot or further than the box? It's closer. So my question on the floor now is, what is the problem
The
exactly?
drawing that they're talking about.
But you were trying to find it. You didn't know what it is.
But I didn't know what it is, so that's why the drawings will be like that in the questions, you know. I wasn't drawing it to scale or drawing it accurate. I didn't know what it was. As I'm just saying, this is a distance D1. That's why we call it D1. Yeah, it's just a distance. So please don't take the diagram them as literal as that, okay? It was just a distance D1 that we didn't know. So we find it out and we find out that it should be very, very close. Are you understanding now?
Yes, exactly.
Alrighty. And Ramona, you want me to go over everything again? All right, let's do this.
But clear the board. I don't want to see it.
Don't rub off the tongue.
Okay, all right. So write off. What you writing off on your like clear the board?
Okay.
Or Ramona, you want to do a different one?
So you have a problem going over the things, sir?
No, it's not an excuse.
I'm not going to write
you
something
believe.
I don't understand.
Also,
So
you have
now I
one-
don't know what
Okay.
to write because
All
I
right.
don't understand what's on the board.
Okay, all right, I get that, and I want you to come with me, please, because you're assuming that my intentions are nothing but pure when they are just that. Okay, I was worried that
You
maybe
just wanting to not
this
go over.
maybe
That's what
pardon me?
I'm saying.
Okay, Ramona, come here, my darling, come here. All right, you don't have to come. I'll talk to you. Okay. Okay, what you're doing right now, Ramona, is you are having a self-defeating kind of attitude. Okay, I'm trying to explain to you that I only suggested that we do a different scenario because I was worried, and I'm feeling bad not being worried for you, that maybe this entire scenario was confusing you. Okay, so I was going to just erase this and do a new scenario. Not because I don't want to go this over. Okay, if I do this the entire time, I still want to get. Okay, so I am deeply offended by your notion that my intention was nothing but pure. Okay, I was actually looking out for you. Okay, so I don't appreciate the attitude at all. Okay, at all.
Sir, please be encouraged.
I'm gonna go over everything, you know. Bird tired, bird can't go anymore.
I thought you were trying to draw a sheep and I was thinking the moon, but it's like it was around the world.
So gravity too strong for the bird.
Yeah, gravity, too much gravity acting on the bird. All right. Now, let me make sure that my thing is proper now. This is the mass. This is the bird. I'm gonna say the bird has a weight of W. I don't know what it was before, so don't shoot me. So let's call it W. Oh, let me check. What was it? 2? No, was it W2 or W1?
W1.
So W1. So I mark the distance, and that is D1. That we don't know. So the drawing is just showing you that D1 is that side from the pivot, but we don't know if it's far away or we're just representing it arbitrarily. Okay, good. Then this is D2, and the box has a weight W2. Okay, M1 was 600 grams. We good? Was M1, right? Okay. So therefore W1 is equal to 6 newtons. I do have to go over how I did all of the 6 newton, Ramona. Up to that part of them. And she holding her eyes while I'm asking her a nice question, and I'm even putting on a little smile and everything. All right, I just go over everything. So, so we know that W is equal to M times G. Therefore, W1 is equal to M1 times G. M1 was 600 grams. We have to convert that to kilograms. Okay, by dividing by 1,000, so this is 0.6, sorry, kilograms. Okay, so therefore the weight becomes 0.6 times the 10. It gives us 6 newtons. So that W1 is now 6 newtons. We good?
Yeah.
All right. So now we need to find W2. W2 is equal to M2 times G, and M2, I don't write it down yet, but M2 was 150 grams. Okay, which is equal to 123.15 kilograms. Therefore, W2 is 0.15 kilograms times 10, which is equal to 1.5 newton. Now we have W2. We're on the same page. All right. And the equation says, or the principle says that the sum of the anti-clockwise moment must be equal to the sum of the clockwise moments. So then we ask ourselves, okay, between the bird and the box, what is causing the clockwise moment? What's causing the anti-clockwise moment? Realize that the bird, if the box isn't there, okay, and the pivot is, fixed, okay, the bird goes and lands on it, it will turn like that, don't it?
Yeah.
So this is what, clockwise or anti-clockwise? This is anti-clockwise, okay? Anti-clockwise movement. And if the bird isn't there, and we put a box on this side, it will swing like so, right? And this is clockwise movements, okay? Clockwise movements. We're good to go. So therefore, anti-clockwise movement, the formula for moment is what? Force times distance. Force times distance. But we have to be specific about the force because it wasn't the ordinary force, it was because of the weight. So we can say weight times distance, weight times distance. But the same thing so far? Yeah. To make our lives easier, to differentiate them, we say this is W, which is the anti-clockwise caused by this. So it is W1, and therefore this is D1. Okay, it's equal to W2 times D2. Then we can plug in our whatever we have now. W1 is 6 newton times D1, which is what we want, is equal to W2, which is 1.5 newton, times D2, which is, what do you say, was 0.1? It's 0.1 meters. Are you with me so far?
Yes, sir.
Good. So we now end up with 6n times D1 is equal to 0.15 Newton meter. So therefore, D1 is equal to 0.15 Newton meter. divided by 6 newtons, which is equal to what you get, 0.025 meters. Okay, and we were saying that is pretty close to the it means that the bird will be pretty close to the pivot. And I was asking, is that logical? Is that sensible? Is that what we expect? Okay, and that is what we expect because the bird has a greater weight or greater mass than the box. So just like how Mr. Bowman had to go closer. No, what to go closer? Yes, Mr. Bowman had to go closer in that scenario there. See where the bird has to go closer to keep it balanced. You good to go? All right. So write off that while I think of another scenario that we can practice. Okay. And this one I'll try to kill up a student. Don't know which student yet. As a matter of fact, I do know which student. No.
We should check our address.
Can't keep his mouth shut all evening. You, Kurt.
My time
I tell us your time. And when I say it's your time, it's your time. Did you have a killer again?
Not quite. We can if you want.
I need your permission. I intend to. Okay, my friend. It's in the water. The attitude, it's in the water. It's my phone. Everyone who knows me know that they don't talk to me until after 9. Okay? No, she calls, so it would have been a call. She's the only one that calls.
Your mom?
Hey. Who calls anybody nowadays? She's on WhatsApp now, but she likes to call. No. Tell me about your life and what's something at work and blah blah blah. Then I said, call me back. And I call back and I'm driving. That way I don't have to listen to it. Mm-hmm.
It finished? Like the whole thing finished, or would it just fine?
It's finished. We just want to know what distance the bird has to be for it to be balanced, for it to be in equilibrium.
Okay.
So we've done, we found the distance, which was 0.025 meters.
So that's good. It's the center of gravity. And if I do it, actually use the actual weight to determine the mass of the object.
Come again?
The center of gravity.
Yes.
That's what you use to determine the mass of the object.
You mean generally?
Yeah, generally.
No. If you want to know the mass of something, you would put it on a chip beam balance and measure the mass of it.
In this scenario.
I made up those values, you know.
No, just asking a question.
Yeah.
This is the part you're doing now, calculation. You answer the first question. The second one can't be the same, but it's just that I want to find out if the weight of the item. You understand? The mass of the item from the center of gravity based upon that question.
Okay. Okay. Let me see if I understand your question.
Because
asking if we consider the mass
distance from the pivot to the center of the box, the distance from the bird to the pivot, and vice versa. That's why I ask you the center of gravity. The weight of the item to the center of gravity from determine the mass of the object.
No.
Okay.
No.
You follow what I'm saying, right?
I'm not sure. I'm not sure. So that's why no. I am. But
You're not determining mass in this any at all.
No, you have the mass.
Each object already has its mass, and then they went on to the seesaw.
It's the middle part of the burden, that's what I ask, you know.
All right.
line where you draw?
Yeah, I am drawing it from the center of gravity.
Yeah, yeah.
Right. But you're using another term, you're saying mass now. Center of gravity.
It's the weight.
The center of gravity is the point where the weight seems to act. When you're asking a question, you kept on saying mass. So that's why I was a little bit asking what exactly you're asking. So, to answer your question, which I think you're asking me, if the center of gravity is taken from the earth, yes. And that's where the weight seems to act. Yes. Okay.
Flamingo.
That's the lamp of my masterpiece or anything there, book. Total bullshit. I can erase now?
No, I can't do it.
Tell me slow, people. Oh, yeah. Yeah. I like her.
Oh yeah?
These are like terrible.
No, I'm like that kind of.
I get over it. And college helped that because I had 2 college mates. Quarter this size. So my section would be like 2 minutes and then their section just like so. I had 4 years to get used to it. So yeah, I think I was doing it. So I'm kind of rigid now, but different ways.
We can adapt a little bit.
Yeah. And I had to, especially teaching, I had to learn to. No, I can't control every aspect. And I'm gonna erase now. All right, so current. All right. I feel present at the moment. All right, so let's see how this will work now. Oh, thank you.
There's one hairstyle.
Can't believe your style, that's your style, okay. No, okay.
Oh. Oh my goodness.
Jesus.
Is that true?
Oh my God. Oh my God.
You said
he's not dead. But he's not dead actually.
Right.
It's not dead.
So where does she need to stand to say?
So.
Oh, she's going to be like, apologize.
No, she's going to go to
No, she's going to go to the end so he can fall to the ground and not.
If you just go to the end, you're gonna hang more.
No, it should come on. It should come
She
needs to come all the way across.
Oh, maybe go
All the way down.
If you go
Yeah.
Leave. Because in that long, you're coming away.
thing.
I think the whole idea is to hang him, just having a social skill.
Alright, alright, so, alright, so, here's the scenario now, okay? Let me do it in my head first to make sure that he survives. Alright, so,
who is hanging?
this is Kurt, this is Sitsi, and that's Miss Campbell, alright? So let's do this. Miss Campbell, weight is, W1 is, no offense, let's say 100 Newton, okay? W2 is, let's say 120 Newton. W3, 150 Newton, okay? Alright. Is let me. Alright, so draw this, okay, and underneath that, pretty much. Which you wouldn't be better. You'd be like. Alright, so I want to get you to think. So give me a second. Yes. All right. So I'm going to say. All right. So that's the diagram, right? In the diagram above. I mean, you can leave a space and write what I'm saying now. In the diagram above, it will be there for a while. Just me, not going anywhere. In the diagram above, the plank. Huh? You have to leave now. Where you going? Where you live? Thailand. But every week, somebody will go downstairs. First of all, it's too early, okay? I can't further my criminal further than physics. Same as Lake here. Oh, that's why. In the diagram above, the plank, this is the plank. The plank is uniform. The plank is uniform. Yes, comma. The plank is uniform with a length of 10 meters. With a length of 10 meters. Okay? The length of 10 meters. The pivot is at the center of the plank. The pivot is at the center of the plank. W1 is 200 centimeters from the edge. W1 is 200 centimeters from the edge. And W3 is at the other edge. And W3 is at the other edge. Like right at the edge. Okay? Good. Oh, I'm not so wicked, man. Just put him on a box. He's so wicked.
Okay.
Okay, for, no, not for, where should W2 be placed? Where should W2 be placed for the system to be in equilibrium? Are we all agree? I'm really going to not say something. Okay. Okay. Where should W2, where should she stand? Okay, where should W2 be placed for the system to be in equilibrium? You have 5 minutes.
Where should
Okay, welcome back. Okay. Where should W2 be? Okay, I can go what position? Okay, for the system to be in equilibrium. Five minutes. Please pay attention to everything that I say. Thank you. Let me see who was listening. You know that issue contact last night. Somebody died. You can what? You can answer?
Right.
4 minutes. Next week class, what I'm going to do is next week class, I'm going to walk with some some charts and stuff. And we're going to have a kindergarten class where we teach each other how to convert from centimeters to meters and say the alphabet and things like that. There's some nursery rhymes. Jack and Jill went up the hill. To buy a pack of weed.
I like Jack and
You can see the weed there in the place. Yes, it should be. My questions will make you think, because that's what physics requires. Yes, ma'am.
Oh, it is too.
What's up?
It's 2 point something.
Yeah, we need. Just focus on it, but we need to know where W2 should be placed, what distance it should be placed for the system to be in equilibrium. By the way, hold up, let me make this clear, okay? Remember, I don't know what the answer is. So even though I draw W2 there, it can be over here or over here. Do you understand? I don't know what the answer should be. So don't let the drawing mislead you, okay? Okay? Like let's say you get it at, I don't know, 100 meters. That's what I'm going to say, okay? Know that it can be at 100 meters because I don't know what the answer should be, okay? Okay? Let me see why are you converting 20 meters how much weight? How much
That means them there 3 meters.
See, what's the math teacher already?
But you wanna,
Sir.
Not two.
so anyways,
Still have to finish?
No, three.
3575.
No, let me check what you do. Look at you using your kidneys. Look at you using your kidneys. I don't know if your answer is correct because I didn't with the calculator, but what you did look sensible. You start yesterday. The exam is time bound, okay? So think fast. Okay? Do something fast. Know the time to make the mistakes. Don't be afraid to write foolishness. Write something on your paper, make a mistake, learn from it, move on. You will learn how to shift your thinking if you do something on the paper. But if you do nothing, then you won't know what to shift, how your thinking is incorrect, and so on and so on. But don't be afraid. Get in zeros now. Okay? And you get your 7 in the exam. Sorry, it's not what 8. All right, 9.
122.
Boy in the army. And boy in the Air Force. Boy in the Navy. Oh, Kimberly has told you.
So I can't explain it, but I think I should be like 2.5 meters from the table.
Well, without the explanation, that means nothing to me.
Well,
I have to see you calculating it on your paper.
I just have to say
And you get laughed at by drawing. What?
I did not know what you're doing.
because, sir, I used to be.
You're
This
missing.
has a moment of 300 and this has a moment of 600. There's so much that is.
What is, you see? And that's why you get one problem. You don't listen to the wonderful teacher. The teacher says, write the equation. Then you put in the things in the equation, then you do the calculation, then you find your answer. What's the equation? What's the first thing you should write, miss?
The sum of.
Did you write that? Write it. And you might see a mistake. Write better down there so, and you might see a mistake. That's how I always write.
Sum of.
No, sum of T.
I always say anti-clockwise movement.
Sum.
Do all of that, right? Sum of ACM is equal to sum of
Yes.
CM.
CM.
After says no. What is causing anti-clockwise movement?
The girls.
No, girls.
The girls are anti-clockwise.
The girls. How many girls do you have?
No, but sir, that's why I say I minus this.
Minus
To
what?
get what she needs.
Minus what?
Okay, this is one girl.
Right.
Right? So
And the other girl.
No, that's what I'm saying. The other girl is 120. So to get the 300 that short over here is like I have to multiply her newtons by 2.5 meters. That's why I'm saying that. What is her 100. So sorry to confuse you. I just kind of need to know.
I see how you're doing it, but
120. No, it's 300 divided by her newton. That's why I said she's 2 point. She needs to be 2.5 meters. So I still write it.
yeah,
I just
when you write so then you can talk. Because I don't know what the answer should be, you know.
She needs to be 2.5
No, I
meters.
don't logic.
Alright, sir. Sir, let's get it.
Oh. Almost got it, but you missed something.
2.5.
You missed something. Okay, you may you not speak something. Okay, check the first line. But you are everything is okay, but because that's one thing you miss. It throws off the answer.
I know how to write
Basic
it.
math you can do.
Sir, I know how to write it.
Alright, let's go. Let's do it. Alright, so here's what you expected to realize, okay? So the entire plank is what? What length? 10 meters. So therefore, what is D3?
5.
Are we all in agreement?
Yes, sir.
What is D3?
5.
5. What did they say about W1?
She's 200 centimeters from the edge.
So this is the edge,
Which means
okay?
she's 2
And she's 200 centimeters. What's the first thing you're gonna do with that?
Convert.
Convert it to meters. So therefore she's 2 meters from the edge.
She's 3
So
meters away.
what is D1?
3 meters.
3 meters.
Right.
All see that? I deliberately did that to see if you remember that this, whatever distance you get, it is always from the pivot. So I deliberately do this to see if you just said D1 is 200 and go about your business, which isn't true, okay? Should always be from the pivot. So it means that she's 3 meters from the pivot. And what they want to know what D2 is. The D2 we don't know.
Right.
Okay. Here's what I expect you to do. I expect you to say is sum of the anti-clockwise moment is equal to the sum of the
Clockwise movement.
clockwise moment. You want to say page so far? Okay. Then you talk to yourself, what is causing the anti-clockwise moment?
W1.
W1 and
W2.
W2. So the moment would be W1 times what?
D1
Times D1 plus
W2 times.
is equal to, yeah, but I can't look in your head. I don't know if that's a new student. Is that the last name, Kimberly?
You?
Is a daughter, miss? You give me peer trouble, you know, peer trouble.
That's not true.
It's true, yeah, I got a report.
Not true, mommy.
I got a report.
I'm joking, I'm joking. But it's so short, like never. Alright, is equal to what? Equal to what?
W3 times D3.
Thank you.
And you
So what's W1? 100 times 3 plus 120 times D2 is equal to 150 times 5. And what is this equal to? 750, I'm hearing?
Yeah.
750 Newton meters. And what is this equal to? 300 plus 120 D2. So therefore, I put this over here. I don't want D2 by itself. Everybody with me?
Yes.
So this goes over here, becomes a negative. So we have 120 D2 equal to 750 minus 300, which is equal to 450. So D2, you know, let me do it the wrong way. 120 D2 is equal to 450. I want D2 by itself, so I divide that by 120, and then whatever I do on one side of the equal sign, I must do on the other side, divide by 120, that cancels that, so I end up with D2 is equal to 3.75 meters, which means that Stuart was correct, while Sitsi can do math.
Okay, sir. I should have followed your
Right, because what you're doing, you were just exactly.
Yes.
There's a reason why I said trust. Everything I do is for a reason, okay? Right. Because I know you were doing the right thing, but because you were putting it down in a proper order, it was just good. I care that. Right? So so it means that she needs to be, so this one is 3 meters. So no, but this one was 3 meters and this one was 3, so she needs to be like, you know, like somewhere here.
7.5.
Yeah. But I don't want to mess up the drawing. But we understand?
Yes, sir.
We understand? Alright, good.
Sir.
Sir,
Who's Barbara? You're talking? Yes.
Can't be thrown off.
By? Sorry,
The
sorry.
first part.
By what?
The first part. W1. The W1 is 200 centimeters, right?
From the edge.
From the edge.
Right.
All right. W2.
That's the Newton.
We don't know where it is. That's what we're trying to find out. And I did say, don't make the position on the diagram confuse you, okay? But me? Even after I said it, I don't know where it should be. Okay, I'm putting it somewhere, something's random on the diagram. Okay?
The W2 and the D. The W2 and the D2.
Interesting.
Yeah, what about it?
Okay. So then D3 and W3 is unknown. That's why I put the equal sign.
Is what?
W3 and D3 is unknown.
It's contributing to the clockwise movement. D3 would cause clockwise movement. But to kick away the box, okay? And he's hanging now, the tire will swing like that, which is clockwise.
Oh, so the two persons then would basically add up.
Right. Mhm. Which is why it's important to say some of the anti-clockwise movements equals some of the clockwise movements, because it can be more than one thing contributing to the movements. Okay. All right. Cynthia and then Ms. Campbell, your question? Okay, yes, Ms. Campbell.
I'm wondering, what is D1?
Why is D1 3 meters? Okay, because remember, we measure distance always from the pivot. So the entire thing is 10 meters, which means pivot to edge is 5 meters. She is 2 meters away from the edge, but the distance is always from the pivot. So if she's 2 meters from the edge, then she's 3 meters from the pivot. And I deliberately did that to see if persons are paying attention to what they should be doing. But the distance is always from the pivot. So look where the force is acting, look where the pivot is, and that perpendicular distance, that's what you use. Alright, so I don't really get to look at momentum today. Probably get started, but we can move on to center of gravity. I'm searching my mind if we don't have anything with more moment. Yeah, okay, we'll probably need to do more questions standing by. Center of gravity and instability. So let me know when you finish writing this off. Giving you about another minute or so. Slow folks might need 2 minutes. Elizabeth, you finish writing it off?
Suppose you could possibly get a question and answer finally.
You're not doing the test.
Should I repeat those or
I'm happy to read it. You will learn now.
Sure.
Yeah, substance. Simple 1, 2, boom, bang, boom, bang. And I'll always do this in the questions that I make up. I'll always make them a little more, for you to, think. Because in my home experience, that's what physics requires, okay? You have to be a thinker, right? I'm not saying you have to be the smartest person alive, just use your brain, okay? And we live in a culture where we honestly don't use our brain so as much as we probably should, okay? We hear somebody say something and we run with it. We don't want to take the time out to investigate. I wonder if this was actually true. Okay? You hear something and just run with it. Remember the last time you thought of something profound and actually go and Google it and search for an answer? Truthfully.
When I remember.
I'm not talking about what they how much weed you have to smoke before I pass out. I'm not talking about that.
Sir, I know. Way too much.
Oh, you've tried it.
Certain things in life, sir.
It depends on.
Someone said knowing things, what you say.
I don't realize they're doing anything at all. Because that would be my next question. What did you sort of say? You don't cut nothing. And a bunch of doing CSEC physics. I'm assuming that it's in alignment with your career path. Okay? So if it's in medicine or engineering or aviation, all that requires thinking and dedication. I'm not just training you for the exam. I would like to think I'm training you for life.
So part to the engineering at UTech requires cake, is it?
Which makes sense.
It does.
I think they can erase no see anybody right thing except for Dean.
Okay, can go ahead.
Huh?
Can go ahead.
Okay. Alright. So Kurt, come here. Come here, man. And the lazier you are, the more I'm going to pick on you. So if I can only listen now, next week I'm picking on you again. Alright. Oh, if you don't want to be in the camera, come right here there.
So I'm still not the camera.
No, they can't see you beyond.
Yeah, that's a blue line.
Alright, so you can go there. Alright, so you're gonna put your legs close together. Okay, hands by your side. Okay, and you're gonna stay in a position no matter what I do to you. No matter what you say. Alright? No matter what you say. Okay. Closer together. Closer together. Alright, you say that. Okay, so no. I mean, closer together. Good. Don't move no matter what I do to you. Alright. So this is an object. Okay. That's all is right now. So this is an object, okay? All right. Now notice what happens when a force is applied, okay? And this is where I'm going to apply the force. All right. So don't move up. Stay rigid like that. All right. Stay rigid. All right. So the force is applied. Oh, this is okay. So when the force is applied, look what happens. I said, don't move no matter what I do.
Keep your form.
Keep your form, man. All right. Alright, so we're going to apply a force. That's what happened. Okay. So I apply a force. That happened, alright? Okay. I apply the force, and that happens. You see that? Let me show you again. Alright, don't move. So when I apply a force to the object, it became unbalanced. It was tipping over. Okay. Now, come over here now. Come over here now, man. Trust me now. Trust me, man. I would never do anything dirty. Trust me. All right. So keep your form. Okay. What can he do now to his form? Okay. So that when I push him, he's stable. Do it. No, don't just do it. So you realize that what he did. What he did was he widened the base. Okay, right? Now, let's say he wasn't able to widen the base. Keep your form again. All right? I'm back to the light, you know. Okay, so let's say I add some mass to him. Okay, right? And let's say I add some more mass to him. Back to the light, man. Sure. All right. You come up 2 pieces of gold in here, right? So let's say add some more mass to him. Okay. What you realize that even slightest, well, what should happen is the slightest touch should cause him to topple over. Now, how can he use these mass to become more stable? What could he do to use these masses and become more stable so that when I push him over, him don't topple over. Distribute the weight. What can I do with these masses to make it more stable? I could lower them. I'm hearing. So I could like tie them around his legs, right? So if I get this bag here and I tie it around his leg, okay, I'll just put it on. Okay. All right. Do you think that would increase his stability?
Yes.
All right. So but you're saying yes. All right. What is it? Anybody else think you're an object? Nobody was talking to you. All right, good. So right away, we are already aware of how things become unstable, or we can stabilize them, and so on and so on. Okay, so without even probably knowing about it, we are already exploring center of gravity. Okay, and we manipulate this in our everyday lives. Okay, we just don't walk around with our physics brain. Okay, now what is center of gravity? Okay, now the center of gravity, you can write this down. What is center of gravity? The center of gravity is a point on an object, where all the weight seems to act. It's a point on an object where all the weight seems to act. I need an expensive phone. Anybody? Could you volunteer an expensive phone? All right. I guess it's not as expensive then. Okay, so let's go. Now, this is a uniform object, right? It's pretty much uniform.
I don't even know if our applicant over.
Yeah, it's nothing. All right. So we know that right here has mass, don't it? In the middle of mass, don't it? At this end of mass, don't it? However, I am able to balance it on one finger. We do it over somebody say drop on them. Alright, so I'm able to balance it on one finger like so. Okay. So right now we know weight is acting downwards, don't it? But yet the phone, this side of it, the right side not falling downwards, the left side not falling downwards. So it's almost as if all the weight is where my finger is, don't it? Because what is balancing it is my finger, okay? My finger is pushing up with an equal and opposite force. Whose law is that again? Oh, the fifth one or the sixth one? That's which one? That's the third law, okay? So right now, the weight is acting downwards, but the phone not moving downwards, okay? Because my finger is pushing back up. Okay, so my finger is balancing the weight. So it's as if the weight is just in the middle of the phone, isn't it? And that's what we call the center of gravity. So my finger is now at the center of gravity. And the key word in that there is seem. All the weight seems to act from that point, but we know that that's not necessarily true. It's only because this object is uniform, like that. Are you on the same page, everybody? Yeah. Okay. For the record, it was already cracked. Okay. She will come and send me a bill. So you dropped the phone. All right. So that is the center of gravity. So if we have things that are unstable, okay, we can manipulate their center of gravity to make them stable. For example, I don't know if you've seen the movies or maybe in real life. If you go to like New York or London, they have the double-decker buses. Okay, and what that means, those buses they have to make corners, right? So based on you, I visualize what I'm saying by the way, a two-story bus. Okay, so if they're going to a corner, okay, you know that it's likely to topple over, right? Because the taller something is, the more it is, the more likely they are to topple over as they go around the corner, right? Okay, so what they do is they find a way to manipulate the center of gravity, because it is found out that the lower the center of gravity for something is, the more stable it is. Okay. Anybody have a water bottle in here, or bottle with some water or liquid or something? All right, give me that. Okay. So, for example, and these are things you already know, okay? If I put this like so, we know it is more stable than if you do it like this, right? So we already know that like this, it is less stable. It's easier for me to topple it over than let's say if it were like that. Okay, good. So what we are doing is actually changing the center of gravity as we go along. Let me explain something to you now. Okay, imagine that being a solid three-dimensional object. Okay, we know that the center of gravity would not necessarily be in the middle, would it? Why not? Because a lot of mass is towards the base. So we know that the center of gravity won't be at the center like if it's a uniform object like this pole here. It's uniform throughout. The center of gravity is not necessarily at the center. Because it's like this, center of gravity would be more like that. Can we all agree on that? And because of that, if I should do this, Lord have mercy, why did I draw this shape now? Okay, let's see. Don't laugh.
This up here.
So let's say I invert the same object. Let's say it's supposed to be the same object. Let's say I invert it, okay? We move the center of gravity till somewhere there, don't it? Realize that out of A and B, which one is more stable? A. So why? Because the center of gravity was lower. Okay. When I make the center of gravity higher, it's very, very unstable. So like if you have the double-decker buses, okay, and everybody decides to go up top, okay, and there's nobody in the lower level, they're actually making it unstable. Do you realize? Okay, so what they do is, and there are instances when that actually happens, okay, because if everybody wants to see the buildings, then everybody's going to be on top. So what they do is they lower the center of gravity of the buses themselves by doing what?
Adding weight.
And again, by physically adding weight to the bottom of the bus. And in fact, if you take not further any of those big buses, for example, whereas that the luggage is always placed at the bottom. There's a reason for it. It's physics. Okay, they could have a compartment at the top and put it up there, but it's better at the bottom. Well, one for ease, and two, we're lowering the center of gravity, because the lower center of gravity is the more stable the bus will be, and it sit on the road. Am I making sense?
Yes.
All right. So a way to increase something stability is to lower the center of gravity. One way to do that is by either making the base like actually larger, physically larger, because again, the larger it is, the more mass there will be, or just adding masses to the base if you can change the base physically. Am I making sense?
Yes, sir.
All right, good. Tell me another everyday scenario where we manipulate things, give them a low center of gravity to make them more stable. Any example?
Like if you have your chest of drawers at home and you keep putting a bunch of heavy stuff in the top drawers and in the bottom drawers.
Right. So if I go to your home and I see jeans, okay, I don't know why I would be in your drawer, but let's say I happen to be there for some reason, and I see jeans and DVDs in the top drawer, and in the bottom drawer I see like underwear and socks. I'd be like, no, this person don't study physics. Because the moment they close a drawer with DVDs, right, it's gonna become unstable and it might fall on you. So I'll put the DVDs and whatever heavy equipment I have at the bottom drawer, and put the lighting at the top. Make sense? Any other everyday scenario?
They're doing squats.
They're doing squats.
Widen.
You have to, right. So when you're doing squats, you have to widen your stance to increase your stability. Any other everyday example? Loading a truck. Elaborate on that. Okay, maybe we can elaborate on that. Loading a truck.
Maybe like
They
when
put the load basically at the
they put the heavier stuff at the bottom.
They put the stuff at the tail.
At the tail.
At the tail.
Okay. But in terms of stability,
But sir, if you notice those AMD trucks though, the bottom of the cargo section is actually wider, and as you go up, it goes up. It's more slender. Did you ever notice those delivery trucks? The bottom is wider, and then the top goes down.
Sorry, sir.
I don't know why they don't be the pay my rent. Oh, okay. Like, pay rent. Okay. I've never noticed that.
Yeah, they look a little bit out of shape.
Yeah,
But
the
that
ones
would
that
make
have the two
sense.
sides, have the two sides. So you
I'm not
have,
visualizing that.
no,
So
that
that's-
drink truck, like it only carries like beers and the crates.
Yes,
Right,
true. When they're packing them, they do like a pyramid thing when they're packing them, right? See, physics, okay. Another example? What about race cars? Race cars are very low. Okay.
I was about to say that
Trust me, some of
not
those corners that they
necessarily
take.
race car.
Okay, and even so they still top over sometimes, right? So they make them very low because the lower the car is, the lower the center of gravity and the more stable it just sits on the road. Okay, so that's what and they're very so they look like this, low and wide. Okay, because what you try to do is lower the center of gravity to make them more stable.
That's why Sean
Pardon me?
I was just about to ask you that. So I was going to ask you if
They're closer to the ground.
I must just study on that.
because when you think about
I mean,
a shape like this, as I run away, I'm
let's not go there. All right. So we have three different types of stability. Okay. Or three different ways of looking at stability. So we can talk about stability. Okay. And we said that the lower the center of gravity of an object is, the more stable it will be. So the lower the center of gravity, the more stable it will be. Okay. You have it already? The lower the center of gravity, the more stable you have it. Okay.
The lower the center of gravity, the
More stable the object will be.
That's it. Yo. More? Funny girl, funny girl, funny days though.
Oh.
Go getting 2 for 1 class.
45.
Yeah.
Pretending we have salt.
Okay. So before we go, we're gonna look at the three types of equilibrium that we can have. Okay. Which of these do you think is the most stable?
No, the middle one. No, the middle one.
This
Wait,
one.
Oh, so it was
Has the wider lace and a lower lace
the
on
first one, yeah, first one.
Alright, so this one has what is called a stable equilibrium. This one has
unstable.
it's unstable, so it says that it has an unstable equilibrium.
And then it have a moving.
We see that this one is like it's either we can't say it's stable because if you push it, it will roll. But rolling is it toppling over, so we say it has neutral equilibrium. Okay. And of course, this one is still because the center of gravity is low, but the same thing I would do this center of gravity is now high, so that's why it is so unstable. Make sense?
Yes, sir.
She can use the water.
Sir, what's his name?
Okay.
I want to ask the after class question.
So that's really end for today. Next week we look at momentum. I think it's a math test. Alright?
Test for what, sir?
Your excuse. Test on everything we've done up to this week. Everything we've done up to this week.
So it's okay.
Up to today's class.
Like an oral test?
What I tell my students all the time, the only thing you have to do in life is die, yes?
What?
For me? Therefore, but we recap it today. We've done all the portion.